In this lecture, we're going to be talking about combinatorial problems. The reason why is most integer programs are the result of modeling some combinatorial problem. Here we've written the definition of what a combinatorial problem is. We have three essential objects. The first is that we're going to have some finite set of objects. This can be items, nodes in a graph, jobs to schedule, anything. The objective in a combinatorial problem is to find some subset, S, of these objects that's going to maximize some function, a cost function, subject to some constraints. And because in a combinatorial problem the constraints can be anything, not necessarily linear, we're going to, instead of talking about constraints, talk about a collection of feasible subsets. So F is going to be a set of sets, and each set inside of F is going to be some feasible object. We're going to go through two particular examples of combinatorial problems so that we can get a feel for what they are. The first combinatorial problem we're going to talk about is the knapsack problem. In this problem, we're given some set of items, which we're going to call n. Each of these items has a size and a value. We're also given some knapsack, and this knapsack has some capacity, C. In this case, we'd like to fill our knapsack with as many items as possible so that we maximize our value. The set of feasible sets is going to be any set that satisfies our size constraint. So this is going to be the set of all sets, such that if we look at all the size of the items, we sum up the size of the items inside of this set, it's going to be less than or equal to our knapsack capacity. Our objective is to maximize or find the set that maximizes our cost function. And in this case, our cost function is to sum up the value of all the items in our set. So our combinatorial problem is going to be to find the set that satisfies our capacity constraint. That is, it's one of these feasible sets, and that maximizes our cost function, which in this case is summing up the values. This falls nicely into our framework of a combinatorial optimization problem. The other problem we'd like to look at is the set cover problem. The set cover problem is a little bit different. In this case, we're given some universe of elements. U is just some large collection of objects. And in this case, N, the thing that we're going to optimize over, is instead of being particular items, this is going to be a set of subsets. So this is a little bit more complicated. N now contains all of the subsets, and we're given what these subsets are. What we'd like to do is find a feasible solution. In this case, a feasible solution is going to be any collection of subsets that's going to cover the entire universe. That is, we look for a subset of N, S, and remember, S is going to be a collection of sets. And we want to take the union of the T that are inside of this set S and make sure that this is going to cover our universe. That is, it's a superset of our universe of elements. Our objective is going to be to find the smallest collection of subsets that's going to satisfy our constraint. So in this case, our objective function is going to be the cardinality of S, the number of sets we need to use to cover everything in our universe. So again, this falls into the framework of a combinatorial optimization problem. In this case, our collection N of objects is going to be a collection of sets. A feasible subset is going to be some collection of sets that's going to cover every element in our universe, U. And our objective is to find the set S that has the smallest number of sets that still covers our universe. These are two examples of combinatorial optimization problems, and hopefully they make the idea more clear. While this very theoretical view of combinatorial optimization problems is going to be extremely useful going forward, whenever we need to solve a combinatorial optimization problem, it's a little bit more useful to look at the input-output view. In this view, what we're given is input. Input is something that's going to lie in a data file, where they're going to be the problem parameters that are given to us. The output is the thing that we'd like to generate. After writing some lines of code, we'd like to actually generate something, and this is the output. We can look at both the knapsack problem and the set cover problem inside of this input-output view and maybe get a better idea of what they are and see how it relates to this theoretical idea of a combinatorial optimization problem pulling a subset of items out. Here we have the knapsack and the set cover problem, and I've written the input already. Usually the input for a problem is easy to identify. In the case of the knapsack problem, our input is going to be the size of every item I, Si, the value of every item Vi, and the capacity of our knapsack C. The output, the thing that we're tasked with generating, is sometimes a little bit more subtle and harder to find. Usually it's given to us in the problem, sometimes we need to find it ourselves. In the knapsack setting, the output is going to be a set S of items such that two constraints are satisfied. The first is that if we take all of the items in our set S and we sum up the sizes, it's going to fit into our knapsack. That is going to have size less than or equal to C. The other is that this set S, if we sum up all of the values, all the VIs, this is going to be maximized at this set S. For the set cover problem, our input is going to be this universe of elements, U, and this set of subsets, capital N. This is the input to our problem. In this case, the output to our problem is going to be some set S, a set S, that now is going to be a subset of N, that is, S is going to be a collection of sets, such that, again, two constraints are going to be satisfied. First, the union of all the sets T inside of S is going to be a superset of our universe U. That is, every element of our universe is going to be covered. We also would like this set S to be the smallest such subset. So this is minimized. This is the output for the set cover problem. If we were to write an algorithm or develop an algorithm, we'd like to develop an algorithm that finds this set S, the one that minimizes, that has the smallest number of elements that's going to cover our entire universe.